This is exciting. The end has come for my full exam recordings for this semester's worth of math classes. After this, all I have left is 13 individual videos for this same class for MA265. But right now we're just running through the fall 2019 final exam, which I'll just preface it with this, is noticeably harder than every single other final exam that we've had in the past 3 years. The average on this, I think, was a 102 or 103 out of 200, and I'm told that a 130 was an A. So let's keep that in mind as we get going here. Question 1. Given that the determinant of this matrix here is 120, what is the determinant of this guy? So let's apply some transformations to this matrix to get to this matrix and keep track of how our determinant is changing as we go. So we know that we want some 111s. So let's take this row. That's a column, not a row. Take that column and divide it by 2. We know that dividing a column by 2 or a row will divide our determinant by that same factor. So now we're left with 115 DE 5F A plus 3D B plus 3E and 5C plus 15F. And we said that the determinant of this will be half of that, so we have 60 left over here. Now let's take row 3 and divide it by 5 using the same rule. There we go. So 60 over 5 will give us 12. And what else do we have to do? Well, we know that adding a factor of a column or a row to another column or row will not change our determinant at all. So we see that they've added 3 times this column to that column right there. And so we can get rid of all of that and it won't change our determinant at all. Now, what do we have left here? Well, we see that we're going to need to take the transpose of this matrix because we want 111 eventually as a row on the bottom, and as a column, we're never going to get that. And taking the transpose does nothing to our determinant, so we're left with 111 DEF ABC. Now, in order to get A up to the top and 111 down to the bottom, we are going to have to switch rows 1 and 3, and switching 2 rows will multiply our determinant by -1. So that leaves us with an answer of -12, which is D for 1. And for once, I actually have the answers open in a separate doc on my computer screen that I can look up at, so I don't have to scroll all around like I usually do. So 1 is D. Question 2, let A be an m by n matrix and B be a non-zero vector in Rm, for which of the following statements must be true? If Ax equals 0 has only the trivial solution, meaning that our null space is zero-dimensional, or that our matrix its number of pivot positions is equal to the number of columns of our matrix, then Ax equals B has no solution. Well, just the fact that A has some pivot positions at all means that Ax equals B has to have a solution for at least some B. So the only situation where this would be untrue is if our matrix was oh god, I gotta turn my sound off. There we go. If our matrix was 0, 0, 0, 0, 0, 0 for the R3 example, what this matrix would do would take our 3 basis vectors and map them to the origin. And so that would take all of 3D space, pull it all into the origin, and as a result, Ax equals B would have no solutions because, you know, our output space would only be defined for the origin, and B is any vector that is not on the origin. So this is not true. If Ax equals B has exactly one solution, then A is an m by n matrix with m greater than or equal to n. So Ax equals AX equals B having exactly one solution implies that our matrix is 1-to-1. And in order, not our matrix, the transformation represented by the matrix A. So AX equals B is a 1-to-1 transformation. And in order for A to be a 1-to-1 transformation, then what needs to happen? Well, the columns of A need to be linearly independent. And if the columns of A are linearly independent, what has to be true? Well, let's go back to our three-dimensional our three-dimensional identity matrix here. If we take a look at what our columns span here, well, this spans all of R3. If we add a column, it doesn't matter what that column is, because our first three columns already span R3, we're trying to fit a fourth vector into the span of three vectors spanning R3. There is no place for that fourth vector to go without already landing in the span of the first three. And as a result, we see that just by this pretty quick and dirty example that this has to be true. And this is the Spanning Set Theorem from a while back, that in order to have a linearly independent set, we have to have fewer vectors, or fewer than or equal to, wording's hard. The number of vectors in our set, so the number of columns in this matrix, must be less than or equal to the number of dimensions that we're trying to span. And since they're saying M has to be greater than or equal to n, that's exactly what we're talking about. As soon as n is 1 greater than m, we cannot have a linearly independent set, so AX equals B cannot be 1-to-1. So 2 is true. What about 3? If AX equals 0 has infinitely many solutions, aka the null space of A is greater than 0-dimensional, then AX equals B must have infinitely many solutions. Well, this is untrue. Let's go back to the extreme case we were using before, the 0 matrix in R3, and we said that all that would do would take in all of R3 as an input and output all of R3, but the only point that's defined for that is the origin, because this maps our first basis vector to 0, 0, 0, our second basis vector to 0, 0, 0, and our third basis vector to 0, 0, 0. And so if we take AX equals B for any non-zero vector, that will have 0 solutions, not infinitely many. So 3 is incorrect. What about 4? If A is an n by n square matrix, then AX equals 0 has exactly one solution. Well, this would be true if we had an n by n invertible square matrix, because invertible matrices are both 1-to-1 and on 2, meaning that they span the output space and that their columns are linearly independent, which has this property that we're looking for all of our output. We'll have at least one solution. But if we have fewer than n pivots, so if our matrix isn't invertible, then AX equals 0 will have non-trivial solutions. It will have infinitely many non-trivial solutions, because this whole equation is representing the null space of A, and the dimension of the null space is equal to the number of columns minus the number of pivot positions, and we can't ensure that this matrix will have n pivot positions. So 2 only is our answer for 2. 3, given that A is equal to that matrix there and B is there, what is A inverse times B, all of that transposed? So we'll need to find the inverse of A to start off with. Since this 1 is in a column by itself, we can rewrite the determinant of A, which we'll need to find the inverse of A. The inverse of A as, let's see, 1 multiplied by the determinant that we get by crossing out the row in the column that 1 is in. So we're left with 1, 0, 3, 1. This just evaluates to 1. So finding A inverse, what we will have to do is what? We will have to take a bunch of cofactors. So what that means is we will need this matrix here to help us out, plus, minus, plus, minus, plus, minus, plus, minus, plus. And what we're going to do is take cofactors for every position in this matrix. So what that means is cross out the row and the column for the cofactor that you want, and take the determinant of everything that is left, and then add the sign corresponding to that position from that matrix right there. So the 1, 1 cofactor will be positive 1. What about here? We'll get 0. Well, negative 0 if you want to be cool. We'll get 0 here. Then what about our second row? We will get negative 2. What else? Positive 1. And then 0 here. And then on the bottom, we get 6 plus 1 is 7. Then negative 3 here, adding in that negative sign. Got to remember that. And then finally, our 3, 3 position will have a cofactor of 1. And we're actually not done yet, because our final step is reflecting everything across the main diagonal. So we will get a negative 2 in this position, a 0 here, a 7 in this position with a 0 here, and a negative 3 here with a 0 right there. So we should now be able to take this and multiply it by b, which is 1, 2, 3, and get our correct answer after we transpose everything. And I'd just like to note that we did multiply by 1 over the determinant, but since our determinant was 1, it did nothing. So let's find this. This will be another 3 by 1 vector. We will get 21 minus 4 plus 1, which is 18. Then negative 9 plus 2 is negative 7. So C should be our correct answer. And finally, 3. Okay, there's our answer, and C is correct for 3. 4. Suppose that this set here is an orthogonal set. Which of the following is true? So in order for x, y, z to be orthogonal to both this vector and this vector, we can just take a little throwback to Calc 3 and take the cross product of these two vectors, and that'll pretty much solve the problem for us. So setting this up, we're crossing 1, negative 3, 0 with 3, 1, negative 1, I. Some people write I, J, K up here. I'm not really sure why. Maybe it's to remind them that they have a negative sign for that position. Okay, but we will find positive 3, positive 1, and 10 as our cross product. So any linear, not linear combination, but any constant multiple of this thing, this vector right here, we can rewrite this in the same kind of way that they do up here, as 3, 1, 10 will be mutually orthogonal to 1, negative 3, 0, and 3, 1, negative 1. So which of the following is true? Well, looking over here, x over z, well, if x is 3 and y is 10, or any multiple of those, then 3 over 10, that checks out right there. So 4 is B. 5, we have a linear transformation from R3 to R2, and the set composed of V1, V2, V3 is a basis for R3, where those are those basis vectors. And we're supposing that the linear transformation applied to V1 gives us that vector, blah, 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 for all those other ones. Now, what is the standard matrix for the linear transformation L relative to the standard bases on R3 and R2? So what we should be able to do here is set up an expression. It'll involve taking an inverse along the way of a 3 by 3 matrix, which is maybe more time consuming than actually just guess and checking through our answer choices, but we should be able to solve for this. So since we know that if we take v1, v2, v3 and put them into a matrix, 1, 1, 0, 1, 0, negative 1, 0, 1, negative 1, if we take that and multiply by our standard matrix X, we'll call it X here, actually, let's call it A, why not, that this, and in fact it really should be AX, there we go. So what we're doing here, we're kind of setting up this form AX equals B, but instead of one vector here, we have three vectors, and we're just doing this all at once. So applying this transformation to these three vectors, if A is a 2 by 3 matrix and this is a 3 by 3 matrix, we should get a 2 by 3 matrix out, and that 2 by 3 matrix will be the transformations of v1, v2, v3 all smushed together. Negative 2, 1, 1, 0, and 1, negative 1. So if we multiply the right side of both of these equations, both sides of these equations, both sides of this equation, there's only one equation, by the inverse of this matrix here, we can cancel it out on the left side and solve directly for A. So let's do just that. The inverse of this matrix, we'll need the determinant. That will be 1 times 0, negative 1, 1, negative 1, determinant, minus 1 times 1, 0, 1, negative 1, and then our third bit will have a 0 multiplied outside, so we don't need to care about that. This right here will evaluate to 1, and then this evaluates to math is hard, and I really shouldn't be doing this right now. I'm a little tired. Negative 1, so positive 1, and so we get a determinant of 2. So if we're finding the inverse of this matrix here, we're going to need yet again a bunch of cofactors, and then we will reflect everything over the main diagonal. And just to remind you, the pattern that I'm using for the signs of these cofactors is plus, minus, plus, minus, plus, minus, plus, minus, plus. So our 1, 1 cofactor will be found by crossing out the first row and the first column and taking the determinant of what's left. That gives us 1. Then for this one, we get negative 1 times negative 1, so positive 1. And then for this third position, we get negative 1. Moving down a row, negative 1 times negative 1, which gives us positive 1. This middle position will give us negative 1. Then what about this guy? We get negative 1 times negative 1, so that's positive 1. And then moving down to our final row, we get positive 1, negative 1, and negative 1. Okay, great. We know that we need to reflect everything around the main diagonal, so this inverse is really 1/2 multiplied by 1, negative 1, negative 1, 1, negative 1, negative 1, 1, 1, 1. Okay, if we've done everything correct up until this point, I'm going to kind of get rid of that. We should be able to take this matrix, multiply it by the inverse of the inverse, which is just this matrix that we started off with, multiply that on the right side of the left equation and on the right side of the right equation, and it will cancel this guy out. We'll be left with the identity matrix times A on the left, which is just equal to A, and then we'll be able to compute our result on the right, which will just allow us to solve for A. So this guy right here is equal to A, and I'll factor that 1/2 out. We'll deal with that at the end. This is a 2 by 3 times a 3 by 3, so we get a 2 by 3 output. And what will we have? So computing the entries of this matrix, we will see that we get -2 plus 1 minus 1, so -2, divide that by 2, we get -1. Then below that we get 1 plus 0 plus 1, which is 2. Divide that, we get 1. Moving to our second column, -2 minus 1 plus 1 is another -1 when we divide by 2. And then below it we get 1 plus 0 minus 1, which is 0. Oh, whoops. And then moving to our third column, we get -2 minus 1 minus 1, which is -4, divided by 2 is -2. And then below it, finally, 1, 0, 1, which is 2, divided by 2 is 1. And that gives us, surprisingly, the correct answer. I did not expect that to go as well as it did. That said, it is 100% faster for a question like this to recognize that you can just find your solutions by multiplying or seeing which one of these answer choices multiplies correctly with all three of these transforms to give us the basis vectors that we started off with. So please do that instead. Oh no, and I lied, it's the other way around. You'd have to multiply these guys down. You'd multiply v1 by this guy and see if it equals that and repeat it for all three. Yeah, sorry about that. 6, let V be a vector space spanned by these three vectors. Which statement is true? Okay, so A, U, V, and W must be linearly independent. That's not necessarily true. Let's say that our space is R2 and U is 1, 0, V is 0, 1. The vectors still span the set no matter what this third vector is equal to. So they don't have to be linearly independent. By definition, if we're trying to span R2 with three vectors, they won't be linearly independent, but still they will span the set, and that's the only thing that we care about. What about B? The dimension of... Oh, sorry. I shouldn't have circled that. We just figured out that that's incorrect. Sorry. What about B? The dimension of V must be 0, 1, 2, or 3. Well, by the Spanning Set Theorem, the highest dimension space that three vectors can span is exactly that, R3. And as a result, this is true. This is true right here, because if we had three linearly independent vectors in R3, they would span R3, but if we go any higher, let's say we try to span R4 with three vectors, we're going to get, you know, a three-dimensional shape in 4 dimensions, just like we get a 2D plane in 3 dimensions when we try to span R3 with two 3-dimensional vectors. And likewise, if one or more of the vectors in the set of U, V, and W are linearly dependent, then we will span fewer and fewer dimensions. So we could span 0 dimensions with 3 0 vectors. What about C? U, V, and W form a basis for V. Not necessarily. Just like we saw here, these three vectors span R2, but this one is completely redundant. So this is our basis for R2, and this guy could be completely ignored. So no, this is not true. The dimension of V is equal to 3. Nope, not necessarily. This is an example of three vectors spanning R2. So nope. And the dimension of V is less than 3. Well, no. If we had 1, 0, 0, 0, 1, 0, and 0, 0, 1, just to give you the simplest example, that would span R3. So the dimension of V would be 3. So E is incorrect as a result, and 6, in fact, is B. 7, let's find all real numbers k such that the parallelogram with these vertices has area 6. This is a little bit of a scary question, but if we graph it, we should be fine, because the minute you hear parallelogram, you should be thinking, determinant. So we get 0, 0. We get 2k up here. Then what else? We get 4, 5. 4, 5. And 6k plus 5. K plus 5. So this is drawn a little badly. Yeah, that's not looking very parallelogram-y. But if I drew this any better, you would kind of see that really this is a parallelogram spanned between 2k and 4, 5, and that this point is just where those two meet in the end. So if I draw this a little better, we have 2k, 4, 5, and then that third point is just kind of slightly redundant. So there is our determinant, and wow, I hate this drawing right here, but we got to deal with it now. And as a result, we can express this determinant as this area here as the determinant of 2k 4, 5. And why is that? Because we can think of this matrix as the area that you get when you apply a transformation where you move the first basis vector from 1, 0 up to 2k, and when you move the second basis vector from 0, 1 over to 4, 5. And we're just measuring how much the area changes of the unit parallelogram span between those first two vectors. That would have an area of 1, and by what factor that changes as we move to this other parallelogram after our transformation. So this determinant will give us 10 minus 4k, and we're looking for all of the values of k such that this determinant, which is really the area of this parallelogram, is equal to 6. So that's really the absolute value of 10 minus 4k. And this will work if this inside bit evaluates to negative 6, which it would for k is equal to 4, because we can have negative sign determinants, but their area, if we're just thinking about it geometrically, will still be positive. And then it will also work if k is equal to 1, because then we'll have the absolute value of 6, which is most definitely equal to 6. So 7 is E. Question number 8. We have A here. Which of the following statements is false? This question is an enormous pain, mainly because it's just a lot of computation, but also because it kind of messes with your head and makes you question everything that you learned in this course. So we have -1, -1, 2, and I'm flipping all the values on, flipping all the signs on this right off the bat, because I'm not writing all these negative signs. 3, 1, 1, 0, 1, -2, 4, 1, 4, 6, 3, 0. Let's row reduce this guy. Okay, let's add 2 row 1s to row 3. That gives us a 0 here and a 7 here, a -2 there. What did I say? What are we doing? We're adding two row 1s to row 3, so this will give us a 12 here and a 12 there. Great. Let's subtract row, oh god, I'm going crazy. Let's subtract row 2 from row 1. We get 0, 2, -1, 3, 3, and let's subtract 3 row 1s from row 3. That gives us a 1 here, -6, so plus 3 is 1, 6, -9 and -9, so this will be 3, 3. And then let's subtract 2 row 3s from row 1. That gives us a 0, a -3. I can't even remember how many I just said. We're subtracting 2. Okay, 0, -3 minus 6 to both of these is -3, -3, so we can turn this into a 1, 1, 1, make this a 0, 0, 2, make this a 0, 2, 2, and then subtract here, we get 0, -2, 0. Okay, there we go. This should be in reduced echelon form if we take this row and put it on top of that row and put it on top of that row just to keep things in a little bit of a better order, the way we're used to seeing them. There is our reduced echelon form. And since we have a pivot position in columns 1, 2, and 3, the columns 1, 2, and 3 of this matrix up here should be a basis for the column space of A. Although, as we'll see in a sec, it is not the only basis for col A. So that statement is false. That statement is true, so it's false. You know what I mean. And let's move on. Let's find the normal null space of A. So we can make a vector out of x4 and x5, setting all of this equal to 0. We'll see that making an x4 vector, x1 is equal to 2x4, -2, x2 is equal to -2x4, -1 there, 1, and 0, and then an x5 vector will give us 0, -2, -1, 0, 1. So taking a look up here, C is wrong because that is definitely a basis for the null space of A. Now here's where things get hairy. We can rule out E because we know that since we have 3 pivot positions here and all of these vectors are 3-dimensional, we must span R3. Thus we're consistent for any vector in R3. So we're definitely consistent for AX equals 5, 2, -8. So that's awesome. What about these two that are left over? Well, what are they doing here? Well, they just took our normal null space vectors and flipped the signs on like half of them and didn't flip the other ones, which is extremely sketchy and should start sounding alarm bells. And in fact, this one is false. That's just it's a little too much. You can't just go flipping half these values and expecting to still get a basis for the null space. That'll be a whole nother subspace right there. But for B, why is B true? As far as I can tell, it's true because if you take these 3, smash them together, and row reduce them, you should get 3 pivot positions. And since all we're looking for is for a basis to span R3, because the column space of A is R3, these 3, since they are linearly independent, work as a basis for R3, which is the column space of A. So 8 is D. 9. Let P3 be the space of all polynomials of degree at most 3. Which of the following sets are subspaces of P3? 1. The set of all polynomials P in P3 such that P at 0 times P at 2 is equal to 0. So the polynomials that satisfy this must evaluate to 0 at either x equals 0, x equals 2, or both. So it's really, I don't like this question because you can test closure under vector addition for option 1 and be pretty sure you've tested it fully, but you haven't. What we'll see is if you add a vector like x minus 2 to a vector like x times x minus 2, this guy evaluates to 0 at x equals 2, this guy evaluates to 0 at both x equals 0 and x equals 2, you will get another vector which works for both of these conditions. But what you have to stumble upon is if you add one polynomial that corresponds to a root of 0 for p at 0, and another polynomial that corresponds to a root of 0 at x equals 2, then you add these together, you get one that works for, that evaluates to 0 for neither. So we'll see that this is 2x minus 2. We plug in 0, we get negative 2. We plug in 2, we get 2. So 1 is clearly not closed under vector addition. What about 2, the set of all polynomials p and p3 such that p at 1 is equal to 4 times p at 0 plus 2? So you don't really need to think about it that much to really realize that this set does not need to include, that it just does not include the 0 polynomial, which is one that all of these sets have to include. If we have the 0 polynomial, p at 1 here will just be 0 because we're plugging in 1 for all the t's that all the x's that we have, but there are no x's, so we just get 0, and that's equal to 4 times 0, so 0 plus 2. This does not work, so this does not include the 0 vector, and so it is not a subspace. What about option 3? The set of all polynomials such that p1 is equal to 0 and p4 is equal to 0. Let's think about that a little bit. So because we have things evaluating to 0 here, if we try to plug the 0 polynomial into this, 0 equals 0, that checks out, and 0 equals 0 yet again. Yeah, that should work. So we know that this includes the 0 polynomial. Is it closed under vector addition? If we take something that evaluates to 0 for x is equal to 1, so x minus 1, how about that? And we add it to x minus 4, do we get something that still aligns with all of this? Well, we don't even need to fully expand this expression because this thing will evaluate to okay, I'll actually do it. Why not? Oh right. Oh, I'm dumb. So sorry if you caught that. P at 1 has to be equal to 0 and p at 4 has to be equal to 0. So those polynomials don't work. This one does. X minus 1 times x minus 4. And so no matter what other polynomial we add this to, if we plug in p at 1 to this section of our sum, we'll get 0. If we plug in either 1 or 4 to this section of our sum, we'll get 0. And so that 0 plus some other 0 will still be 0. And if we go grab that polynomial back, we multiply this by any constant, these things will still work. So 3 only is our answer for 9. Sorry, that was a little sloppy there. 10. Suppose that A and B are n by n matrices. Which of the following statements must be true? Well, A is only true if A and B are the identity matrices, which they are not, because I times I is just I. Any matrix times the identity is just itself, and so there's no way to say that this has to be true for any arbitrary n by n matrices. Let's see, if AB equals I, then B is the inverse of A. Well, I completely agree with this. We know that A times A inverse, or A inverse times A, is equal to the identity matrix, and that's the only case that we know this for, and so therefore B has to be the inverse of A. C, if A and B are invertible, then AB inverse must be equal to A inverse B inverse. Well, no, this isn't true. AB inverse is equal to B inverse A inverse. You have to remember to switch the order when you're taking the inverse of multiple matrices at the same time. This also applies for the transpose as well. What about D? Is this matrix invertible? Well, clearly the answer is no. You can evaluate that determinant if you really want to, but you'll see if you try to row reduce it which I did before, you will not get 3 pivot positions. So nope, nope. And then E, if AX equals B is consistent for some B in Rn, then A is invertible. Nope, I disagree with that one. What about this matrix right here? 1, 0, 0, 0. This takes in all of Rn and spits out all of Rn on the x-axis. So it will squish all y values down to y equals 0. So it's consistent for all vectors b that are just along the x-axis here, but our matrix is not invertible. So clearly this guy is not true. So 10 is B. 11. Which of the following are or is true? 6, 5, 3, 1 is in the subspace of the 2 by 2 matrices spanned by those two matrices. So what we should be able to do is find a linear combination of these two matrices, which forms this matrix. And in order to do that, I'm going to kind of unwrap these matrices into 4-dimensional vectors going counterclockwise from the 1, 1 position. So we can express that first matrix as 2, 3, -4, -1, and our second one as 0, -1, 2, 1. And we're making an augmented matrix with this guy unwrapped, which is 6, 5, 3, 1. So we should be able to row reduce this matrix and end up with a linear combination of what am I trying to say? Linear combination of the 4 entries of these two matrices that gives us the 4 entries of this third matrix. Okay, so row reducing. Let's add 3 row 4s to row 2. That gives us a 0 here. We're adding 3, so we get 2 here and 8 here. So this can reduce to 1, 4. Let's subtract 2 row 2s from row 3. That gives us 0 minus 8 is -5, so blah, blah. And let's divide row 3 by 2. So if this was a consistent linear system, 2x1 should always be equal to the same thing. But since we see that 2x1 is equal to 6 and 5 over 2, this is an inconsistent linear system, so 1 is incorrect. What about 2? The polynomial 1 plus 2t plus 3t squared is in the subspace of polynomials of degree at most 3, spanned by these 3 polynomial vectors there. Okay, so how can we deal with this? Well, we don't actually have to do any math, which is nice. We see that this polynomial includes a constant. None of the polynomials we're trying to express it as a linear combination of have any constants in them. So we don't even have to make this into a matrix or solve any kind of system or anything because there's a constant here and no constants here. So there's no way to make a constant. What about 3? This set is linearly independent for all real values of A. Well, let's make this into a nice big augmented matrix 1, 1, 0, 1, A, 3, 1, 2, 0, 1, -1, 1, 0, A, -1, 2. And let's reduce away, see if we can get something interesting out of this. So what should we do? Let's subtract row 2 from row 4. No, let's actually subtract row 4 from row 2. That will give us a 0 here, a 1 here, a 0 here, and an A minus 2 there. What else? Let's subtract row 3 from row 2. That gives us a 0, a 1, and plus 1 here, so A minus 1. And what else is going on? Let's swap around some rows really quickly. what we're looking for is either a case where it's clear that a certain value of A will lead to fewer than 4 pivot positions, or a case where we just have 4 pivot positions and it doesn't matter what any of our values of A are. Let's subtract row 1 from row 2. Nope, I actually don't want to do that. Let's subtract row 1 from row 2. I'll do it, whatever. 0, 2, minus A. Okay, so here we have a pivot position. Here we have a pivot position. Let's subtract row 3 from row 2. That gives us a 0 here and a 3 minus A in that position. So pivot, what else? Yeah, see, this is kind of the spot that I got into when I was actually taking the exam. It was really unclear whether or not this system was fully consistent or linearly independent. Let's see if we can do literally anything else to try to make this any more clear. Let's subtract. Yeah, let's add row 3 to row 4. That gives us a 0 here and an A minus 2 there. Okay, so we are looking for. Okay, I think this actually solves it for us. So we need 2 more pivot positions. The only way we wouldn't get 2 more pivot positions is if these 2 rows were multiples of each other. Then we could use 1 to set the other one equal to 0. And with all these A's floating around, there should be no way to do that. So no matter what, we will always have 4 pivots, and thus 3 is correct. And we knew that 3 was correct for a while now because we know for sure that 1 and 2 are correct. So 3 being a little hairy is okay in this kind of context. So 11 is, in fact, D. Okay, 12, we have A and B being 4x4 matrices such that that is A and the determinant of B is 6. What is the determinant of A, B inverse? Well, the determinant of A, B inverse can be rewritten as the determinant of A times the determinant of B inverse, and the determinant of the inverse of a matrix is just 1 over the determinant of the non-inverse of that matrix. We know that the determinant of B is 6, and so all we have to do is find the determinant of A, which is not going to be fun. Not going to be fun at all, but we should be able to do it by putting it into upper triangular form. So 2, 5, 0, 4, 3, 8, 11, 5, 4, 6, 3, 8, 2, 9, 0, 4. So the only thing that we can legally do in this context to get things into upper triangular form so we can multiply the main diagonal entries of our matrix is add multiples of rows to other rows. We know that that doesn't change our determinant at all. Let's subtract row 1 from row 4. That gives us 0, 4, and 0. Here we could divide that row, but if we divided that row, that would be illegal. So we have to leave it as a 4, but we can add multiples of it to other rows. So for example, we can multiply it by 3 over 2 and subtract it from row 3 to set this to 0, multiply it by -2 and add it to row 2 to set that to 0. You get the picture. So we can set all of those to 0 with different multiples. Let's subtract 2 row 1s from row 3. That gives us a 0 here and a 0 here. And likewise with this 3, we can set this value to 0 as well. So at this point, what what are we looking at? Not much. I should have done this in a little bit more of a thoughtful way. Okay, but I think we should be okay in just a second. Okay, let's multiply row 1 by 3 over 2, so that will be 3, 0, 0, 6, and subtract it from row 2. That will set this 3 to 0, and we'll subtract 6 here, so we'll get a negative 1, which will allow us to set that to 0. Now we can flip some rows. Let's flip those two rows. That'll multiply our determinant by negative 1, so I'll keep track of that right there. So we are flipping this guy into this guy's spot and replacing him. There we go. Boom. Look at that. So multiplying our main diagonal elements, we get 24, well, negative 24. Counting in that negative 1, we get positive 24. We have to divide by 6, so that gives us positive 4, which is B for 12. When I took this exam the first time, I forgot that negative 1 and got negative 4 and got it wrong. 13. Consider the equation AX equals 0, where A is a 5 by 7 matrix. Which of the following statements is or are true? AX equals 0 has infinitely many solutions. Well, we know that AX equals 0 has non-trivial, aka infinitely many solutions, for any nullity greater than 0. So the dimension of the null space has to be greater than 0. We know that the null space of a 5 by 7 matrix must be greater than or equal to 2. Why is that? Because we only have 5 rows to work with, but we have 7 columns, so the maximum rank our matrix can have is 5, and since the rank plus the nullity must equal the number of columns, aka the nullity is equal to the number of free variables that we have, the nullity is at least equal to 2. So as a result, there's no situation where the nullity is 0, so 1 is true. What about 2? The matrix has rank less than or equal to 5. Well, that's exactly what we were just saying here. It can have a maximum of 5 pivot positions. There's no place to put a 6th pivot position. And so, yes, this is true. What about 3? The associated linear system has exactly 2 free variables. Nope, not necessarily. If we had a 5 by 7 matrix that was 1 here and then zeros everywhere else, that has 6 free variables. So no, that's dumb. 13 is A. 14. Let M 3 by 3 be the space of 3 by 3 matrices. Let H be the subspace of M 3 by 3 consisting of all matrices such that A multiplied by 1, negative 2, 0 is equal to 0, 0, 0. What is the dimension of H? Okay, this is a little bit of a weird one. The explanation that I'm about to give sounds pretty correct, and I think it's okay to use in this context, but it doesn't necessarily mesh with some of the explanations I've given in the past for polynomial subspaces, which I'm not saying that those are incorrect. I'm saying that there's some discrepancy somewhere, and I'm not exactly sure where it is. So A, D, G, B, E, H, C, F, I, we're multiplying that by 1, negative 2, 0, and we should get an expression. We should get an expression for really what variables are at work here. So multiplying these together, and knowing that we have to get the 0 vector, or I'll just do 3 by 3 by times 3 by 1 will give us another 3 by 1. Okay, let's just work with that. We will get A minus 2B, D minus 2E, G minus 2H, and this must be equal to 0, 0, 0. So A minus 2B must be equal to 0, d minus 2e must be equal to 0, and g minus 2h must be equal to 0. So here's the thing. This right here must be true, and the answer ends up being that the dimension of h is 6. So 14 is C. And really that seems to just be counting up the number of variables that are in play here. And you can kind of think of each one of these as a line, right? Because we have some variable is equal to some other variable if we move one of those over to the other side. And the thing I don't like about this at all is that it doesn't actually make much sense. I'm still missing something here, but theoretically you're okay just counting up the number of variables at work. I don't like that. I don't like that at all. Yeah, this makes me feel very bad. What I will say to talk about the discrepancy between this and my explanations for polynomial subspaces, there are conditions, if we have some polynomial subspace defined by p at 0 is equal to p at 1, we end up getting an equation. This is actually a bad example. Let's say 2p at 1. That was a different question. We end up getting that 0 has to be equal to C1 plus C2 plus C3 plus C4. And this thing is if you were to plot this would be 4-dimensional. In the way that, okay, no, this is a bad explanation. I'm sorry, I won't go into this now. If you want to see the question that corresponds to this, just look up polynomial subspaces on the spreadsheet. Yeah, and if you know what's going on here, please let me know. This makes me feel very bad that I don't have a good explanation for it. But there we have it. 15, for the system of differential equations given here with a of 1, 2, negative 5, 6, what is the origin? So we need to find the eigenvalues of a. That's solving 1 minus lambda times negative 6 minus lambda plus 10 is equal to 0. Lambda squared plus 5 lambda minus 6 plus 10, so plus 4 is equal to 0. Lambda plus 4, lambda plus 1 is equal to 0, so lambda is equal to negative 4 and negative 1. When we have two negative eigenvalues over time, because the solution to this will have e to the negative 4t and e to the negative t, as t approaches infinity, whatever is connected to these two terms, which is the rest of our solution, will approach 0, and as a result, our solutions will approach the origin, and so we would call that origin an attractor. So 15 is A. 16, consider the linear transformation from R3 to R3 given by these three facts about what the transformation does to the basis vectors, the standard basis vectors of R3. And we're asked to find whether or not it's 1-to-1 for every value of A. So we could form the standard matrix by smushing these three vectors together, and it'll be 1-to-1 if those three individual columns are linearly independent. It's a little tough to see. You can do this first one without actually doing any math if you see that if A is equal to 2, we will have 2, 1, 2, and 4, 2, 4, which are direct multiples of each other, and as a result, the set will not be linearly independent. What about 2? The linear transformation is not on 2 for A equals 2. Well, let's see. If we plug in A equals 2, yeah, we can just think about this visually, actually. So we have one vector. We have one vector in R3. Let's just have it pointing there, v1, and then we have a second vector that is not in the first one's span. That's v2. But we know that for A equals 2, our third vector will be on the span of our first vector, v3. And a linear transformation is only on 2 if it spans the output space. So we want to span R3, but since we only have 2 linearly independent vectors, we're not going to span R3. What about 3? The standard matrix for the linear transformation of T relative to the standard basis on R3 has rank 3 for all real numbers not equal to 2 or 8. Well, since 1 and 2 are incorrect, we know that 3 is true, and you should be able to go in and solve for those values. And I may or may not cut right here, depending on whether or not I figure it out or not. So let's set up that standard matrix: A, 1, 2, negative 1, 3, 1, and for A, 4. A is equal to 8. Well, we know that A is equal to 2 will lead to a matrix with rank 2, not rank 3. But what if we plug in 8? Let's just do that and solve away. Let's subtract 4 row 3's from row 1. That gives us 0 here, minus 5, minus 16, so negative 12. Let's subtract 2 row 2's from row 3. 0, minus 5, minus 16, so, negative 12. Well, there you go. You can use row 1 to set row 3 equal to 0, and this is true. That is true right there, because we will have rank 2 for A equals 8 or A equals 2, so 16 is C. Oh, wait, why did I cross out 2? I'm sorry, I'm recording this too late at night. The linear transformation is not on 2 for A equals 2. We said that was true. We said that was true. So we get D as our answer. Sorry about that. 17. Find the distance from the vector y to the subspace spanned by these two vectors right here. Okay, so in order to solve this, we'll be solving y, which is 1, 0, negative 2, and we're subtracting from that the orthogonal projection of y onto u1. That will be y dot u1, which is negative 4, over u1 dot u1, which is 22, and we're multiplying that by 2, negative 3, 3, which is u1. Now we're doing the same thing, the same process with u2, so y dot u2 is 3 plus 2 is 5, and we're dividing that by u2 dot u2, which is 9, 10, 11. And this is multiplied by u2, so 3, 1, negative 1. And then the absolute value of this entire thing, so the magnitude of the vector that we get, should be our answer. Let's turn this into a plus, make this 2 over 11, and let's multiply. Actually, no, let's not multiply everything by 11. That gets a little bit too sketchy. So we have 2 over 11 and negative 5 over 11. Let's kind of factor these in. We'll have 15 over 11, 5 over 11, negative 5 over 11. We can get rid of that. And then what about over here? We will have 4 over 11, minus 6 over 11, and 6 over 11. So doing this subtraction here, we get 1, 0, negative 2, plus 4 minus 15 is negative 11 over 11, so negative 1. Negative 6 over 11 minus 5 over 11 is negative 11 over 11, so that's negative 1. And we have 6 over 11 plus 5 over 11 is 11 over 11, which is 1. We compute this to be 0, negative 1, and -1. And so the length of this vector will be the distance from our vector y to the subspace spanned by those two, and that's just root 2, so 17 is A. 18, let's consider the following system of differential equations with that initial condition. What is x1 at 2 plus x2 at 2, where x1 is this first equation and x2 is the solution to that second equation. So our solution will be in the form x1, x2, that's bad, x2 is equal to c1 v1 e to the lambda 1 t plus c2 v2 e to the lambda 2 t, where v1 and lambda 1 are a eigenvalue-eigenvector pair, and the same with v2 and lambda 2. Let's solve for our eigenvalues. We'll be solving the determinant of a minus lambda I equals 0, so -7 minus lambda, 8 minus lambda, plus 54 is equal to 0. Lambda squared minus lambda minus 56 plus 54 is -2 is equal to 0. Lambda minus 2, lambda plus 1 is equal to 0, so lambda is equal to 2 and -1. For lambda is equal to 2, a minus lambda I is -9, 9, -6, 6. We can simplify that down to 1, -1, 0, 0, and so we get an eigenvector of 1, 1 from that. For lambda equals -1, we get -6, 9, -6, 9, which simplifies down to 2, -3, 0, 0, and so we get an eigenvector of 3, 2 from that. So we can write our initial condition into this expression. We can set 5, 4 equal to our solution evaluated, and I should specify here, our solution x1, x2 is equal to c1 v1 e to the lambda 1t plus c2 v2 e to the lambda 2t. So plugging in t is equal to 0, we get c1 times 1, 1 plus c2 times 3, 2. Solving this, we can make a augmented matrix. 1, 1, 3, 2 is equal to 5, 4. Let's subtract row 1 from row 2. That gives us 0, -1, -1, so 1, 1, 0, 2. There we go. So C1 is equal to 2, and C2 is equal to 1. We are finding x1 at 2 plus x2 at 2. x1 is equal to just the top half of these vectors, so 2e to the 2t plus 3e to the negative t, and x2 is equal to 2e to the 2t plus 2e to the negative t. So evaluating this at 2, we will get 4, -2, 4, -2, and adding these together, we get 5e to the negative 2 plus 4e to the 4. So C is our answer for number 18. 19, we have an inner product space question. We're finding the orthogonal projection of 10t cubed minus 5 onto the subspace spanned by 1 and t. So the orthogonal projection will just be the orthogonal projection of this thing onto 1 and onto t, and we'll add those together. So that will be equal to 10t cubed minus 5 dotted with 1 over 1 dotted with 1 multiplied by 1 plus 10t cubed minus 5 dotted with t over t dotted with t times t. So let's compute all of these little integrals. The integral from -1 to 1 of these two functions multiplied together, 10t cubed minus 5 dt, well, because t cubed is a function that acts around the y-axis such that if we take an integral equally below and above, you kind of know what I'm saying, so on an equal x distance to the right and to the left of the y-axis, we're just going to get 0. So with all these integrals, any odd powered functions in here we can just get rid of. This -5 will be negative 5t on -1 to 1, which is -5 and 5, so we get -10. I'll replace that up here. Then if we're looking for 1 dotted with 1, that's just going to be the integral from -1 to 1 of 1 dt, so t on -1 to 1. This gives us 1, -1, so we get 2. So this part will evaluate to -5. And really that just leaves us with one single answer choice, because we know that there's no way we're getting a cubed in here, because this will evaluate to a scalar, this will evaluate to a scalar, and we're multiplying by t. So let's make sure that we also get this answer for this last little bit here. Finding the integral of from -1 to 1 of 10t to the 4th minus 5t dt, well, we can get rid of this odd exponent function here and just take 2t to the 5 on -1 to 1. This will give us 2 and -2, so we get 4. We get 4 right here. And then if we're taking the integral of t squared from -1 to 1 dt, we will get t cubed over 3 from -1 to 1, which evaluates to 2/3. So 4 times 3 over 2 is 6, and so we get the 6t that we were looking for here. The easy mistake to make on this question is, instead of computing the orthogonal projection, so I'll call that, I don't know, p hat if this is our polynomial here. Instead of computing p hat, you compute p minus p hat to find, we would kind of call it the distance from that function to the subspace spanned by 1 and t, whatever. That's what I did when I first took this exam, and of course they have an answer choice lined up very nicely for you. It's C, and it's very incorrect. So 19 is E. 20. Which of the following statements is true? If 2x2 matrices A and B have the same eigenvalues with the same multiplicities, then A is similar to B. I fell into this trap taking the exam. And why is it incorrect? Well, it seems pretty incorrect. It seems pretty correct, because we know that saying that a matrix is similar to some other matrix is the same thing as saying that you can say that A is equal to P, B, P inverse, if we're using the A and B that they're talking about here, where B has the eigenvalues of A down its main diagonal, and so since an upper triangular matrix, its eigenvalues are just its main diagonal, so B has the same eigenvalues with the same multiplicities by definition as A, so that checks out. But think about this: what if A is a 3x3 matrix with only 2 eigenvectors? Can you diagonalize it? Can you say that it is similar to some matrix B with the same eigenvalues and same multiplicities? No, you can't, because you cannot put it into this form. We can only diagonalize a matrix if the total algebraic multiplicity of all of its eigenvalues is equal to the geometric multiplicity of its eigenvectors, aka do we have enough eigenvectors to span R to the n if our matrices, well, they're 2x2 matrices, so we would need two eigenvectors. If we only have one, this is not going to work. What about B? Row operations on a square matrix do not change its eigenvalues. We should know this by now. If you do some row operations on a matrix, you're changing its eigenvalues. That's why we're not allowed to do anything to our matrices before we solve for the determinant of A minus lambda I. So that's no good. Or sorry, row operations do not, row operations do change eigenvalues. This one says do not, so it's false. Okay, it's late. See if we can get through the rest of this. C, there exists an n by n non-zero matrix A such that every non-zero vector in Rn is an eigenvector of A. So I read that and I was like, oh my god, that seems so wrong, but I feel like that should be right. I didn't end up picking it. I went for A, even though, you just heard it, there's a pretty good argument why A is false. Let's think about this. What is an eigenvector graphically or geometrically? An eigenvector is a vector that after you apply a transformation, the original vector that you had on that eigenvector only gets scaled by a certain amount, and it's scaled by the eigenvalue associated with that eigenvector. So if we have a matrix transformation that takes our first basis vector that started at 1, 0, and our second basis vector that started at 0, 1, and we just multiply those by 2, so we move our first basis vector to 2, 0, and our second to 0, 2, what have we done? We've just expanded all of space. And so any vector will just be multiplied by 2 after, well, that's a terrible arrow, after our transformation. Thus, every single vector is an eigenvector of A, and these kinds of transformations come in the form lambda I. And you can see this, for lambda equals 2, this situation that we drew here, all vectors are multiplied by that eigenvalue, which is 2. So this is true. What about D? The numbers 1, -1, and 0 can be the eigenvalues of a 3 by 3 invertible matrix. Well, if 0 is an eigenvalue of a matrix, that means that that there is some vector along which values or vectors get scaled by 0. And if they get scaled by 0, that means that an infinite number of them are going to land on the origin, because the span of that vector has to pass through the origin at some point. And because we're ending up with an infinite number of values on our origin, we're not going to have the dimension of our null space will be greater than 0, and as a result, our matrix will not be invertible because we won't have n pivots for our n by n matrix. So that's no good. And what about E? Is this diagonalizable? Well, let's solve for the determinant of A minus lambda I equals 0. 4 minus lambda times -6 minus lambda plus 25 is equal to 0. Lambda squared plus 2 lambda minus 24 plus 25 is plus 1 is equal to 0. This will have solutions lambda plus 1 squared is equal to 0. Lambda is equal to -1 with a multiplicity of 2. If we plug in -1 to A minus lambda I, we get 5, -5, 5, -5. This will only create one free variable. So we can row reduce this down to 1, -1, 0, 0. So we get an eigenvector of 1, 1, but we're still not diagonalizable because we only got one eigenvector. We need 2 eigenvectors from this eigenspace because it has a multiplicity of 2. So yeah, no, that's no good. So 20 is C. 21, we have 2 matrices here. For what value of k, if any, what value of k, if any, will make AB equal to BA? So that's essentially asking us for what value of k will A be the inverse of B or vice versa? But we could go down that route, but let's go down the just brute force method. Let's multiply A and B, 2, -1, 3, 1 by 2, -3, 9, k. We'll get a 2 by 2 matrix here. 4 minus 9 is -5, -5. 18 minus 3k, -9 plus k. Okay, and then we'll multiply these in the other order, and we should be able to just directly solve for the values of k that make this true. Okay, we get 4 minus 9, which is negative 5. That checks out. We get negative 6 minus k. So right off the bat, if these two entries are equal to each other, k must be equal to negative 1. So there's 1. And then let's make sure that that works for all of our other entries. We get 6 plus 9. Let me make sure I'm doing that right. Yeah, 6 plus 9 is 15. And since we have 18 minus 3 k up here, should that be plus 3k? Yeah, that should be plus 3. I'm not sure why we have minus 3, because up here we get, yeah, 18 plus 3k. 18 minus 3 will give us that 15, so that's good. And then finally, for that final entry, we have negative 9 plus k plus k. And negative 9 plus k, no matter the value, is also equal to negative 9 plus k. So A works for both of these. 21 is A. 22, consider the basis S for R3 given here. Let's apply the Gram-Schmidt process to find an orthonormal basis. Great. Okay, so we can always, for the Gram-Schmidt process, take the first vector of our set and normalize it to find our first basis vector. So I'll call this U1, U2, and U3. And let's do this. V1, our first basis vector, is the normalized version of U1. So 1 over the magnitude of U is 1 over root 5 times 2, 1, 0. So now V2 is going to be U2, 0, 1, 2, minus U's projection onto V1. So that will be U1 dot, sorry, not U1, U2 dot V1 over V1 dot V1 multiplied by the vector V1. So what you'll see is that in computing this, 1 over root 5 will be multiplied twice on the top of this expression and twice on the bottom, so we can completely ignore it. Let's multiply, or take the dot product of V1, discounting that 1 over root 5, with U2. That will give us 1. And then V1 dot V1 gives us 5. And then we have V1 here, which is 2, 1, 0. We can, since we're normalizing this in the end, it doesn't matter what factor we multiply everything by. Let's multiply everything by 5. We get 5, 10 here, so we can get rid of that. And this is equal to negative 2, 4, 10. We can simplify that down to negative 1, 2, 5. And the magnitude of this is what? 25 plus 5, so root 30. There is our second one, and we already know our answer there because that's the only one that has the 1 over root 30 that we're looking for, and it already corresponds with V1 correctly. But let's find V3 just for the hell of it. So we'll take U3, which is 2, 0, 1, subtract U3's projection onto V1. That will be U3 dot V1, discounting the 1 over root 5, so we get 4. We're dividing that by V1 dot V1, which is 5, multiplied by V1, which is 2, 1, 0, and then we're subtracting V2, and I'll circle this one too, V2 dot U3, which gives us negative 2 plus 5, which is 3, divided by U3 dot U3, and by U3 I mean V2 dot V2, which is, yeah, 30. So this is 1 over 10. I'll turn this into 8 over 10 for later, and this will become negative 1. This will be multiplied by V2, which is negative 125. Okay, multiplying everything by 10, we will get 20, 10, minus 8 times all this, so 16, 8, and yeah, we're just subtracting that. Okay, let's compute this right here, normalize it, and we should have an answer. 20 minus 16 plus 1 is 5, is it not? Yeah, 5. And this will be negative 10 and 5. Okay, so normalizing this, we get 1 over root 5, no, sorry, 1 over root 6, 1, negative 2, 1. There, okay, that works. So 22 is C. 23, consider the inconsistent linear system here. We're finding the least squares solution of this system. So that will be found by finding A transpose A x is equal to A transpose B. Let's compute A transpose A, 1, negative 1, 1, 0, negative 1, 2, multiplied by A, 1, negative 1, 1, 0, negative 1, 2. This will give us a 2 by 2 matrix with entries 3, 3, 3, 5. And then A transpose B is 1, 0, negative 1, negative 1, 1, 2. Multiplied by B, 6, 0, 0. Gives us a 2 by 1 matrix of 6, 0. Okay, we can make an augmented system from these two. 3, 3, 3, 5 is equal to 6, 0. Make this 1, 1, 2. Subtract 3 row 1s from row 2. And we get 5, negative 3. There we go. And yeah, that is 23 is B. Okay. 24. We're taking A to the 2019 power. Aren't they really cool with that very relevant power right there? I wonder if we'll get a 2020. Maybe. We'll see. So we know that if we can diagonalize A, we can take A to the kth power and set that equal to P d to the kth power P inverse, where D is a diagonal matrix and P is an invertible matrix formed from the eigenvectors of A. So let's find the eigenvalues and eigenvectors of A. We're solving 7 minus lambda times 2 minus lambda plus 6 is equal to 0. Lambda squared minus 9 lambda plus 14 plus 6 is plus 20 is equal to 0. How will this factor? Lambda minus 4, lambda minus 5 is equal to 0, so lambda is equal to 4 and 5. Great. 4 lambda is equal to 4. A minus lambda I. A minus lambda I will be 3, negative 6, 1, negative 2. So we can simplify this to 1, negative 2, 0, 0, and get an eigenvector of 2, 1. For lambda is equal to 5, A minus lambda I gives us 2, negative 6, 1, negative 3. We can simplify this to 1, negative 3, 0, 0, and get an eigenvector of 3, 1 out of it. So we can set up A to the k is equal to our matrix P, which is these eigenvectors 2, 1, 3, 1, times the diagonal matrix with these eigenvectors corresponding eigenvalues. So we have 4, 0, 0, 5 to the k. And then we need to multiply by the inverse of this first matrix P. Well, that inverse is going to be 1 over the determinant of that matrix, which is negative 1. So 1 over negative 1. We'll flip the A and the D position, so we get 1, 2, and flip the signs on the B and C position, so negative 1, negative 3. But factoring in this negative 1, we're just flipping all of our signs over again. Okay, we're kind of sort of halfway there. We're computing A to the 2019, so we can replace K with 2019, multiplying a diagonal matrix by itself. We'll just square all of the powers. That doesn't make sense. Square all the entries. So taking something to the 2019, we'll just take all of the entries to the 2019 power. Okay, computing left to right because I feel like it, 2, 1, 3, 1. We are multiplying that by the result of this multiplication here, which will be minus 4 to the 2019. Let me just make sure. Let me just make sure that I'm on the on the right track. 24 is. Hey, yeah, we should be good. We should. I shouldn't be checking at this point. And on the bottom we have 5 to the 2019, and then over here we have 3 times 4 to the 2019, and then down here we get minus 2 times 5 to the 2019. Okay, now multiplying these together, we get a 2 by 2 matrix with what? 24. Okay, we're good. Negative 2 times 4 to the 2019. Ooh, that's ugly. And this is going to need to be even bigger. Come on. Even bigger. Then on the bottom plus, not the bottom, I'm losing my mind. 3 times 5 to the 2019. Now we're really on the bottom. Minus 4 to the 2019 plus 5 to the 2019. And at this point we already know our answer is A. This is the only one that matches up with what we've computed so far, but just to destroy me even more, let's compute the last bit. We get 6. That's a 9. That's a 9. We get 6 times 4 to the 2019 minus 6 times 5 to the 2019, 3 times 4 to the 2019, and finally minus 2 times 5 to the 2019. Okay, everything checks out, I think. Yep, and A is our correct answer. Okay, I got this one wrong for a very easy to fix reason, and let's figure out why. So what we're doing here is an orthogonal diagonalization of this matrix in here, and they're already giving us the eigenvalues of that matrix there. And if you're familiar with the form that orthogonal diagonalization takes, this should make a little sense what they're writing here. So we know that the matrix Q such that A equals Q D Q transpose, which is the same as Q inverse, because Q will be an orthogonal matrix where all of our vectors, all the column vectors, are orthogonal to each other, and they're also of unit length. Because I'm really losing my train of thought. For an orthogonal matrix, Q inverse is equal to Q transpose. That's the property that allows us to diagonalize with a transpose instead of a normal inverse, because they're exactly the same thing in this context. But these column vectors will be the bases for the eigenspaces of this matrix right here. But the important thing to know is that the spectral theorem of symmetric matrices, which that matrix right there is because it's equal to its own transpose, the spectral theorem says that 1, all symmetric matrices are orthogonally diagonalizable, which is exactly what we're trying to do here. But more importantly for our purposes here, so we don't run into the wrong answer choice, the eigenspaces of a symmetric matrix are always orthogonal, but that doesn't mean that the vectors that we get within individual eigenspaces are automatically orthogonal. So we're going to have to orthogonalize those on our own. So let's get to it. We know that our eigenvalues are 1, 4, and 4, but for the sake of my sanity, no, we're going to do it all. We're going to do it all. For lambda is equal to 1, we will get 2, 1, negative 1, 1, 2, 1, negative 1, 1, 2. Let's simplify this thing down to find the eigenbasis. or really just the single eigenvector. Let's add row 3 to row 2. That gives us 0, 3, 3. That'll become a 1, 1. Let's subtract it here, 0, 1. Let's add 2 row 3s to row 1. That gives us a 0 and a 1. We can use row 1 to set row 2 to 0, 0, and we'll switch that over. So we see that ooh, did I mess up a sign somewhere? Nope, I didn't. Okay. If we solve this and pull out our eigenvalue normally, we'll see that x1 is x1 is equal to 1 x3, which is our free variable, negative 1 x2, and 1 of itself. So there is our eigenvector. We can normalize that 1 over root 3, and that should be the vector corresponding with this first column in these matrices here. And we see that A and B are the only ones left that actually work for those. Now you could be really cool and clever and take a look at A and notice that, okay, well, this guy looks good, but the dot product of our second two columns is not 0. It's not 0 at all. It's what, negative 1/2. So you could just go rule out A, or you could be like me and choose A and get it wrong. Those are your two options. Pick very, very carefully. So for lambda equals 4, we can find, hopefully, 2 vectors in that eigenspace that are orthogonal. And by the spectral theorem of symmetric matrices, those will automatically be orthogonal to this guy. And we won't even have to do any more work for that, which is awesome. So plugging in 4, we get negative 1, 1, negative 1, 1, negative 1, 1, negative 1, 1, negative 1. We can use row 1 to set row 3 equal to 0. Oh yeah, and we can set row 2 equal to 0. I'm going to flip these signs, and we're ready to solve. But instead of solving normally, like normal people, we are going to write this as an equation. x1 minus x2 plus x3 must be equal to 0 because we're solving a minus lambda I equals 0. So we do really have a right side over here. So this must be true. Let's find some simple values for which this holds. Well, if x1 is 1 and x2 is 1, then x3 can be 0. So 1, 1, 0 is a vector that works for this. Now, if we want another vector that satisfies this, let's flip x1. Why not? Sounds like a good plan. So if x1 is negative 1, x2 can still be 1, and that means that up here, or actually all over here, both of these vectors must be orthogonal because it doesn't matter what's in this position. It's multiplied by a 0 when we take the dot product, and these two dot to 0 as it is. So x3 must be, well, if we have negative 1 here for x1, and then this x2 is also negative 1, x2 has to be 2. X3 has to be 2 in order to compensate. So these two vectors, you'll see, are the two vectors that they came up with here, 1, 1, 0, and negative 1, 1, 2. But really, you can come up with whatever vectors you want, but it's good to kind of get used to this process, which is, I'm pretty sure, what they're kind of doing behind the scenes, which is what gives them those two vectors there. And yet again, since we have one eigenspace of vectors here, one eigenspace of vectors here, the spectral theorem tells us that these are automatically orthogonal to each other. And you can go test it, but it is true. And as a result, we don't need to do anything else. We're done. And this exam did not go particularly well for me, but that makes sense because it's the hardest one in the last X number of years. So, okay, I get to go edit this, which is going to be a whole lot of fun, but I appreciate that you stuck around for this.